Good afternoon, or this is good morning, I guess. And we have it's a real pleasure to be here. So this is joint work with Babichenko and Peretz, who at the time were students in the Hebrew University. Now they're both postdocs, and they're game theorists. Sousi, a probabilist in Cambridge, England, and Peter Winkler, who's in Dartmouth, and many of you know. So this is about two topics that I find both interesting, but perhaps the most enjoyable is the connection between them. So which is a kind of unexpected connection. Similarly, unexpected connection. Yesterday evening, as I was stepping to a restaurant, there was Jean Bourgain. So so he said, "This time is too early for me, too early for him, but I should tell him there what I'm talking about today." So anyway, so let me start with the reminder of Kakeya sets, and the game will appear later. So these have been investigated a lot, especially here in the finite field setting, but I'm going to go back to the most classical setting of R2. So a set in the plane is a Kakeya set. More formally, this is a Besicovich set, but I'm going to blur this distinction. So I'll just call it a Kakeya set if it contains a unit segment in every direction. And Kakeya's question was to find sets of minimal area of this type. And he really wanted to be able to turn the segment, but this is I said I'll ignore this distinction. So what is the smallest area in which you can have a unit segment in all directions? And Kakeya had a candidate, this three-pointed deltoid, and you can easily see that you can indeed turn a unit segment inside this. And he asked whether it's the smallest area possible. The answer was given by Besicovich, who actually first looked at this question independently. And the answer is a very resounding no, because you can get areas of sets of arbitrarily small area in which you can turn a unit segment, and even a set of zero area which contains a unit segment in every direction. So this is what Besicovich showed. And he gave a deterministic construction of such a set, which was later simplified by Perron, Schoenberg, and even later was shown to have really spectacular consequences in harmonic analysis by Pfefferman. So it's been a major topic of study in harmonic analysis. Let me just show you pictures drawn by Terry Tao of one of these constructions, the Perron construction. So let's start. So formally, what you have on the left, it doesn't contain a unit segment in every direction, maybe, but 45 degrees. So if this is a right angle triangle and a right triangle, and the base has length 1, then of course you have 45 degrees. And then if you take a union of 4 rotations of this, you'll get segments in all directions. So we're going to ignore this difference between a quarter Kakeya set and a full Kakeya set. You can always take 4 rotations. So this is essentially a Kakeya set in this formal sense of containing a segment in every direction, but of course has very large area. Now, suppose you split this by connecting this point, the apex, to the midpoint of the base, and then shifting the resulting triangle a little bit. So you'll get this shape. And note that all the unit segments all the directions that were covered here are still covered here, right? But the area is smaller because we've created some overlap. And you can repeat this process. So take each of these 2 triangles, split them in the same way, and shift optimally so as to minimize the union of the areas. And you can continue this way. And after repeating this kind of thing 8 times, you'll get a union of lots and lots of triangles with relatively small area. It turns out that it goes down like 1 over log n if you have n triangles. And this is the classical construction. Now this shows sets of arbitrarily small area. To get, 1 second, to get 0 area, you need to be able to embed such constructions inside one another and take a limit, which is not an obvious thing, but was still done by Besicovich. Yes?
I think the slide should move a little to the right.
Yes, I don't know if that's within my capabilities here. So, maybe it is. Okay, good.
To be clarify, I mean, if I take disjoint segments in every direction, they're going to make 0. Do that be connected? What exactly is the definition of this?
No. The union, if you take disjoint segments in every direction, and well, you have to then you have to still describe exactly how you take them, because the union should be measurable. So, but if you just take disjoint segments in every direction, there's no there's no reason for the area to be small. Remember, you have uncountably many directions. Yeah. What? We're talking about compact sets. So,
because if they're not compact, I think I mean, measurability using some analytic set argument would be not so difficult.
Okay, we can discuss that. That later. I mean, the point is to get zero area. But really, you can think of this as a problem with real finite content, in the sense of, instead of talking about 0 area in the limit, suppose you can measure this by saying you want it to contain a unit segment in every direction, and you want the epsilon neighborhood of the set to have small area, as epsilon goes to 0. So this is something you can measure. Okay. So I'll show you a probabilistic construction that arose kind of by accident. So it aroses from this game that was studied before, and I'll give references shortly. So the game has 2 players. It's a search game. It has 2 players we'll call the hunter and the rabbit, and they move on a graph. The graph has n nodes. The rabbit can jump from one node to any other node or stay in place, so there's no restrictions placed on the rabbit. The hunter can only move to adjacent nodes on the graph or stay in place. We'll start by looking at the graph, which is a cycle. Turns out, if we understand this graph, we'll get a very good handle on the general graphs. So think of it first on the cycle, but with a view towards the end of going to more general graphs. Now, they don't see each other at all. So they don't see each other until they land in the same spot. So think of it as the game is happening at night. Okay. So again, the hunter chooses a spot, the rabbit chooses a spot, they don't see each other, and they start moving. The rabbit by arbitrary jumps, the hunter only staying in place or moving to adjacent site until they land on the same site, and then the game is over. Okay. And so at time 0, they both choose initial positions. At each subsequent step, the hunter moves to an adjacent node, and the rabbit can go to any node, and the game ends at capture time. Okay? Now, this is a zero-sum game where the hunter aims to minimize capture time and the rabbit aims to maximize capture time. It's not a bounded game, so there aren't finitely many strategies, but it's easily related to a bounded game. So let me quickly explain that relation. Oh, these are some references. So this is the original paper where this game was analyzed. This is our work, and these are some of the classical references on the Cakeya sets. Okay, so here's a finite game that really captures the issue of this infinite game. So let's run this the interaction of the rabbit and the hunter for only n moves. So n is the same as the length of the cycle. And and just have payoff 1 to the hunter if he captures the rabbit in these n steps, and 0, payoff 0 otherwise. So now it's a finite game. The number of pure strategies available to the rabbit is just n to the n, or n to the n plus 1, because he has to choose an initial site and then jump n times to other sites. While for the hunter, it's just maybe n3 to the n. He has to choose an initial site and then choose where to go, but he also has 3 options at every move. So these are the pure strategies available to them. But in this kind of zero-sum game, it's easy to see that to play optimally, they both will need to randomize. So they'll need to choose some distribution over their pure strategies. And then the von Neumann-Minimax theorem tells us that there are optimal randomized strategies for both players. And just as a reminder, if you play an optimal strategy, it doesn't hurt to declare to the opponent what this strategy is. Of course, you don't say exactly which pure strategy you take, which path you take, but the distribution can be declared, and it doesn't hurt the player. So in other words, there is some value to this game, and the value is just the probability of capture under optimal play. And the rabbit has an optimal strategy so that ensures no matter what the hunter does, the probability of capture will be at most this value. And this, for the same value, the hunter has an optimal strategy that ensures no matter what the rabbit does, the probability of capture is at least this v. OK, so let's call the value of this game, this finite game, p or pn. This is the value of the finite game, which is, as I said, just the probability of capture under optimal play in this finite game, gn star. Now, if we go back to the original game gn, which was still on the n cycle, but the goal there was to look at the capture time, then we're going to ignore constants. So the capture time there is about n over p, so of order n over p. And it's easy to see that because so suppose the rabbit has a strategy which ensures probability of capture at most p, whatever the hunter does. So what the rabbit can do, it just iterates this strategy. So it plays for n moves according to the strategy, probability p of capture at most. And then another n moves, just repeats an independent copy of the same strategy. So again, probability of capture at most p. So the number of rounds until capture will be geometric. So the time until capture will be at least n over p. Now, for the converse, we know the hunter has a strategy, randomized strategy, that ensures probability of capture at least p. He can't exactly iterate that in every round because the strategy would typically say, in the first step, start at a random location, and he can't jump that far. But what he can do, he can waste a round. So he plays optimally for the first n steps, so he has probability of capture p. Then if in the next round he's told to start at some random site, he will waste a round of at most n steps to just walk slowly to the next location he's supposed to start. And then, in the third round, he will capture again with probability p and so on. So by wasting a factor of 2, he can ensure capture in time 2n over p. So we're going to ignore constants, and this shows that these two games are very closely related. Okay, so if the probability of capture is p in the finite game, then the length is n over p. But the real issue is, does p depend on n, or is it going to a constant? So in other words, can the hunter ensure capture in linear time or not? So just to set the stage, let's say some obvious things. So certainly the rabbit has many ways to ensure capture time at least n. So one way, you can just choose a random node and hide there without moving. So then the hunter has to explore order n nodes until he finds that. So that will ensure capture time at least n. But Also, the hunter, just by sweeping, will capture in time n against that strategy. Another easy thing is if the rabbit jumps to a uniform random node in each step, so then it doesn't matter what the hunter does, and he will capture in time n. So we see the rabbit can easily ensure capture time at least n. What about the hunter? Can he ensure linear time, or what's the best he can do? So the trivial upper bound for the hunter is n squared, because he can choose a random location that will catch and start there. That will catch the rabbit with probability 1 over n. And then he can choose another random location, and he will be there in step, and then walk slowly towards that point. And so he will ensure probability of capture 1 over n every n steps. This is extremely wasteful, but it gives an upper bound of n squared. So, okay, so these are some trivial bounds. Now, this talk I've learned, is much better with audience participation. So, can you propose suppose you are hired as consultants by the rabbit and the hunter. What do you propose to them to do? They're supposed to devise their own strategy, but as I said, if a player plays optimally, then it doesn't hurt him to even declare the strategy. So, in other words, a good strategy should work no matter what the opponent does. But let's just think of it less formally. I mean, you're placed in this situation. What do you do? As one of the, yes.
The rabbit picks a random location. You should probably stay around there longer, because the probability will be far from the hunter, and then open time.
So can you be so what do you suggest? He picks a random location and then
Either for case steps and then pick another one.
Okay, stay there for okay.
Square root of n.
What?
Stays there for square root
Stay
of n.
there for square root of n, and then that's and then jumps to another random location. For sweep for the hunter in our talking. So start somewhere random, and what do you mean by sweep? So you go, just go right, but for how long? If you go forever, so maybe it's reasonable as a strategy for the game of length n, but for the unbounded game that would not work well if the rabbit does the same. They can sweep like that. But say sweep for order n moves and then change direction, right? So this is the natural guess. So call it the zigzag hunter strategy. What? No, they don't see. That's why I had this picture of the dark night. They don't see each other, right? So
It's not really a repeated game.
It's not interactive.
That's right.
As a consultant, you would probably advise the rabbit to get a flashlight.
That's right. They have to respect the rules of the game. So anyway, one natural thing is the hunter starts in a random direction, as Jeremy was saying, and switches direction with probability about 1 over n. So one should say that for the hunter, just doing a random walk is not a good idea, because it would take him time n squared to reach the other side. So that's, but this zigzag hunter strategy has some randomness, and so he walks for order n steps, but geometric of mean n, and then turns around. He should also occasionally just stop to remove periodicity, and this is the strategy we first guessed that this should have a linear time capture, because it seems, what can the rabbit do after this kind of, against these random sweeps? Turns out he can do something, and the true answer for this strategy is n to the 3/2. Let me explain that. So here's the rabbit counter strategy. So from a random starting node, the rabbit walks root n steps to the right, then jumps 2 root n to the left, and repeats. So let me show this in a picture. So this is the hunter's, this is space-time diagram. Time is going vertically. And this is what the hunter is doing. So he's walking basically to the right. Very rarely, like in frequency 1/n, he either stops in place or switches direction. So this is the path of the hunter. So for order n, he is walking in the same direction. Now this is the rabbit counter strategy, which is walk root n steps to the right, then jump 2 root n to the left, and repeat. And this is all happening on the cycle, so that's why you have this periodicity. Okay, these are the strategies. Now, when would this rabbit be caught by this hunter? So let's look at one round. So in one round, in n steps, the hunter is basically just going in one direction, maybe switching direction once or twice. So really the issue becomes this rabbit strategy when it's going to be hit by a random line. Now, if the random line is going to the right, then there are only root n different lines here. So for a line, for a random line to hit one of these, it has probability 1/√n. If the hunter is walking to the left, then observe that this path is contained in the union of these a strip of width root n. So again, there's only 1/√n chance for a line to the left to hit this rabbit. So this rabbit will be caught in one round only with probability 1/√n. So you'll need root n rounds. So the capture time is n to the 3/2. By the way, this is the optimal counter strategy to this hunter strategy, because you can. So the reason is whatever the rabbit does, his path will consist of n points in this square. And if you have a set of n points in the square and you project it in 2 orthogonal directions, one of these projections had better have at least root n points. And this means that any set of points here, if you hit it by a random line from the left or the right, it will intersect the set with probability at least 1/√n. So, so n to the 3/2 is the answer for this zigzag strategy, but it's not optimal. So any suggestions to the hunter how to improve? What was the weakness here of the hunter? Always the same speed. Thank you. So the speed was too predictable. The hunter should randomize his speed as well, and start at a random point and continue at a random speed. And so there are several ways to implement this. Here is one. You take independent uniform variables, and you at time t, you're at an plus bt, integer part, mod n. So an represents the uniform starting point, and bt represents the movement at a random speed b.
So
okay?
Is a hunter has a chance to move at different speeds?
But the speed is bounded by 1, because he cannot jump more than one step at a time. So he chooses this b uniformly at random at the beginning. So we're just describing what happens in one round. He chooses the speed b uniformly at random at the beginning of a round, and then he walks at that speed in the round. What does it mean? He follows just a straight line path, but since he has to stay on the lattice, he takes the integer part of this, and the slope is at most 1, because he's restricted to be Lipschitz. He can't move more than one step in one time. Okay, this is the hunter strategy, very similar to what we had before. He doesn't even need to change direction here, and he sweeps, but not at his maximal speed. Okay. So it's very tempting to say, I want to catch this rabbit as fast as possible. Let me move as fast as possible. But it takes some willpower to move slower. So what capture time does this yield? So the best way to calculate this is with the second moment method, or one easy way. So let kn be the number of collisions until time n. So even though the game stops when they meet, let's just artificially continue it for a full round of n steps and count the number of. So the rabbit is now allowed to do an arbitrary strategy. And kn counts the total number of collisions in n steps with this straight line Hunter strategy. Okay, and so we're going to calculate first and second moment and show that the probability of kn is positive at least 1 over log n. Kn was the number of collisions with this Hunter strategy. Now, because of the uniform random starting point, the marginal is uniform at any time. So at any specific time, the location of the Hunter is completely uniform. So the probability of colliding at time I is exactly 1 over n. So the expected number of collisions is just 1 in a round. So what about the second moment? So you expand second moment. It's the diagonal term just is identified with the first moment, and then you have a sum over I different from L of this correlation, probability of collision at time I and at time L. And it's enough to show that the second moment is bounded by log n just by the usual second moment inequality, this consequence of Cauchy-Schwarz that tells the probability of kn positive is at least the first moment squared divided by the second moment. Okay, so it's enough to show the second moment is bounded by log n. And for this, to prove this, it's enough to show, to bound these correlations, probability of collision at time I and another one at time I plus j is going to be bounded by 1 over jn. Once we show that, then summing over j will give log n over n, and then summing over I will give a log n. So this is what you want. Another way to interpret this is, given that they collide at time I, the chance of another collision a few steps later, j steps later, is at most 1 over j. And this is kind of easy to see geometrically or by writing down the equations. So maybe maybe I won't go over that in detail, but it's very easy to see just the property of random lines. And again, anyone who wants can show this later. So then once you know that, then you get the second moment bound, and the probability of collision in n steps is at least 1 over log n, and which gives a capture time of at most order n log n, right? Because probability at least 1 over log n rounds, the number of rounds needed to capture will be log n, so this gives an n log n upper bound. But still, the question is, can one do better than n log n? And if you don't find anything better for the Hunter, then the attention has to turn to the rabbit. What do can the rabbit do better than linear time? And it's the two extreme strategies for the rabbit either hide all the time in the same spot or jump. They both lead to n. So it turns out that the rabbit does have a strategy at most 1 over log n, and we're going to. We haven't yet defined the strategy, but the way, once we define it, the way we're going to bound the probability of collision in n steps is by extending the strategy to 2n steps and bounding this probability by the ratio of these expectations. So clearly, the expectation of number of collisions in 2n steps is at least the probability of colliding in the first n times this conditional expectation. So rewriting, we get this inequality. And now, so the idea is we're going to have the rabbit do a random walk, but it won't be a simple random walk. So he won't jump 1 step at a time, and he won't jump the maximum. He'll do something intermediate, which we'll see. So because of that inequality before, which is almost an identity, let me go back. Right? So the expected number of collisions in time 2n, if the rabbit is going to start at a uniform point, and at every time, individual time, he'll be a uniform point, this numerator is just going to be 2. So the issue is, in order to decrease the probability of collision, he wants to maximize the number of collisions. So this is kind of the revenge of the rabbit. He wants, if he's captured, he wants to collide many times with the Hunter in order to minimize the overall capture probability. One way to think about it is that you have a collection of all possible paths, and the rabbit doesn't mind if he collides once with the rabbit. He doesn't mind if, when we artificially extend the path, if there are many collisions after. And he wants to kind of concentrate all the collisions in as few paths as possible. So this is, the goal is really to maximize this expected number of collisions, given that there is one in the first n steps. And so think of the rabbit and the hunter. Once they collide, the rabbit wants to ensure that they would have many collisions after. Now, what does he know about the hunter? He doesn't know where the hunter will be. The hunter could use any strategy. But what he does know, the hunter is slow. He can only move at a linear speed. So in order to increase the chance of capturing him, the rabbit also wants to keep moving at a linear speed, but still be kind of at as unpredictable as possible, given that restriction. So what is a random walk that moves at linear speed? You know, ordinary simple random walk has diffusive speed, but suppose you're summing random variables and you want these partial sums to grow linearly. What random variables would you sum? Cauchy. So this is to emulate a Cauchy random walk. So Cauchy distribution is not on the integers, but you could take integer part. But there is a better way than to take integer part and to remember what one construction of a Cauchy random variable is to say, let's start Brownian motion at a unit distance away from a straight line and look at where you hit this straight line. Okay, and this, the hitting distribution is exactly a Cauchy variable. And then if you put another straight line at a distance 2, the hitting distribution here will be, has two representations. One is it's the sum of two Cauchys, because you hit here and then you hit here. And another, it's just a Cauchy scaled by 2. So you see from this picture the scaling property of a Cauchy variable x1 plus another independent copy will have the same distribution as the variable at time 2. So this is the stability property of the Cauchy distribution, one stable. And what we want is to take some kind of discrete version of that with the same behavior. So we want the probability that Ri equals L for all L between minus I and I to be like 1 over I. So this will be this kind of one-dimensional linear decay. And once we have this property, then we'll be able to see that the number of collisions in 2n steps, given there is a collision in the first n steps, is going to be bounded below by a sum of 1 over I, so by log n, and then we'll get that the probability of collision in n steps is bounded by 2 over log n, constant over log n. So for Cauchy random variables, we know that the sum is spread over, well, it extends further on, but in the interval minus n, the density is bounded below. So to get this in the discrete setting, what we do is we actually simulate that construction in the discrete setting. So finally, what the rabbit will do, he'll do a kind of the following. Maybe I'll draw it here. So he'll draw a lattice. So remember, this is a cycle. So this is periodic. So these 2 points are identified. But let's kind of draw this piece of the Z2 lattice. And the rabbit, so this is time 0. This is where the rabbit is now. And he has to determine where to be at time 1. Okay, so this is this jump distribution. In order to determine it, he's going to do a thought experiment of walking on this space-time diagram. So he's going to do a random walk on the space-time diagram. Let's see, do we have any colors here? And until he reaches the line t equals 1. When he reaches it here, this is the spot he's going to jump to. And then he repeats this. Maybe in the next round he happens to move directly up. Then he will go here. And then maybe in the next round he goes like this. And so on. So at every time, in order to determine where to actually go, he will run this simple random walk in kind of Z2, where the first coordinate is mod n, until he first reaches the line 1 above in time, and that's where he'll actually jump. Okay, so this exactly simulates the story we had there for Brownian motion. It simulates it for a random walk. And then once you do that, it's quite easy to see, one can do it from local limit theorems or just for symmetry considerations, that the distribution has the property I mentioned. So for any point between minus I and I, right, so if we want to see what is the probability that the walker at time, say starting from 0, that at time I, he will be in location ki, then you just have to run the random walk in the lattice and see what's the hitting probability of this point. And the hitting distribution here up to constant is uniform. So it exactly gives the property we wanted here, that after a collision, the probability of the rabbit being in location L I steps later is going to be at least 1 over I. And so the expected number of collisions will give the log n. And so there is a simple argument by symmetry to really show that this 1 over I bound holds. And okay, and once you know this bound 1 over I, then you get expected number of collisions log n in 1 round, and hence the probability of colliding in a round is at most 1 over log n, and so the number of rounds needed for collision is log n. So we found a strategy for the rabbit that ensures capture time at least n log n, no matter what the hunter does. So in all this analysis, we're not restricting the hunter to use the previous strategy I described. The hunter could do anything, and the probability is, and the capture time in expectation is at least n log n. So coming back to Kakeya sets, it turns out that Kakeya sets arise from any good counter strategy of the rabbit to the previously described hunter strategy. So to describe this hunter strategy, so remember we took A uniform, and it doesn't matter in 0, 1, or here I'll take it in -1, 1, it's equivalent, and B uniform in 0, 1, and let the hunter be at time t in location an plus bt. So okay, and then we measure a collision if the rabbit and the hunter coincide. What is the chance there is a collision in the time interval m to m plus 1? So collision in this time interval means that the rabbit at time m is between an plus bm and an plus bm plus 1, because there is an integer part to take. And we can represent this event in parameter space. So here is the parameter A determining the initial location. This is the parameter B. Since they're picked uniformly, then the distribution of AB is just normalized area measure on this 2x1 rectangle. And the event that there is a collision at the time interval mm plus 1 corresponds to these parameters AB being picked in this triangle. Now you can see more clearly what the rabbit wants, at least as a counter strategy to this hunter strategy. What he wants is to choose, he can choose these RMs, and he wants to, if he knows he's facing this hunter strategy, which we already showed is essentially optimal, then what he would want is to minimize the union of the areas of these triangles. And so these triangles can be thought of as, so if the rabbit was staying in place, then you'd get exactly n triangles of this form. So they all have base 1 over n, and they just tile a right 1 by 1 triangle. But this is if the rabbit was staying in place the whole time. The rabbit can move, and his movements correspond to moving these triangles, because again, in this picture, the base of the triangle is Rm over n. So in other words, the fact that we found a rabbit strategy that ensures capture probability at most 1 over log n, so that's ensured against any hunter strategy. But if we employ this hunter strategy, we know 1 over log n is the truth. So what this means is that against that when the rabbit plays this Cauchy strategy, the union of these triangles will have expected area 1 over log n, because that's the capture probability in a round. So, and that's the same up to constant as the optimum that can be achieved with n triangles. So if you have n triangles of length 1, and you want their union to be a Kakeya set, then you can achieve small area, but the best you can achieve is 1 over log n. That's classical fact. And this random construction up to constant matches the optimum. And except a small Kakeya set will give a strategy against this specific hunter strategy. But a small Kakeya set, noted, we have deterministic Kakeya sets, and a deterministic strategy for the rabbit would never work against all hunter strategies, because the hunter might do something that's effective against this particular choice. So any Kakeya set corresponds to a good strategy against the random speed hunter strategy. But the Cauchy strategy we described before for the rabbit works against this and simultaneously against all hunter strategies. Okay, so towards the end, I want to say what happens when we pass to the limit in this construction and then go back to infinite graphs. So I told you before that Besicovich already constructed such sets that have 0 area by a clever kind of recursive embedding, but he never gave a formula for a Kakeya set of 0 area, or a Besicovich set of 0 area. And this process, passing to the limit, allows us to do so. So let me show you that. So first, what's a Cauchy process? So if you run a planar Brownian motion and look at the first time where it hits the line at height p. So height t is the height now, not the time for the Brownian motion. It's the height. And when it hits this line at height t, call its location xt. Okay? So this is a realization of the Cauchy process. So you can also construct the Cauchy process directly. So this is this Levy stable process where the okay, but it's nice to think of it in terms of this representation. Okay. So again, so the Cauchy process has the property xt plus s minus xt. There is a typo here. It has the same law as sx1. And x1 has the Cauchy distribution. Okay, now here is the Kakeya set. Look at all points of the form a xt plus at, where at are in 0, 1. So I claim this is, again, a quarter Kakeya set. It contains all directions from 0 up to 45 degrees. So that's easy to see, because if you fix t, what do you have here? When you fix t, then you let a range from 0 to 1. You just have a line of slope t. So we have here lines of all slopes from 0 to 1, and the xt just corresponds to a translation of this line. So it contains lines. Now what about the area of this? The area of this is 0. To see this, we slice the other way. When you fix a, what you have, when you fix a, then you're slicing this set in the first coordinate. And then you have the path of a Cauchy process, a biased Cauchy process. And it's a classical fact, follows from old results of Keston, but is easy also to prove directly, that the Cauchy process and its biased version have 0 length on the line. It's closely related to the well-known fact that the planar Brownian motion, the path has 0 area. And very similar proof gives that the Cauchy process and also this biased version, xt plus at, for any fixed a, if you look at this, it's a set on the line. It has Hausdorff dimension 1, but 0 length. And if you know that, then you get that this, just from Fubini, that this set will have 0 area. So it's something that follows in 3 lines from classical results. But as far as we know, and we've, I think, checked quite extensively by now, this is the first formula for a Besicovich set that can be written explicitly without any recursive definition. And one thing that can also be shown, this Kakeya set is optimal in the sense that the epsilon neighborhood has as small a Lebesgue measure as possible, 1 over log epsilon, which again is known to be best possible. Okay, so the proof is a simple calculation, which I'm going to skip. And finally, I want to say something about general graphs and an open question in that regard. So we just talked about the cycle, and I made claims about general graphs. Let's see how that relates. So first, on any graph, there's clearly a lower bound of n, just from the rabbit jumping arbitrarily or hiding. Those strategies still apply and give a capture time of at least n. Now let's see that there's an upper bound of n log n that applies for all graphs. And the reason in any graph on n vertices, of course, I'm just talking about connected graphs, then you can pick a spanning tree and look at the depth first search on the spanning tree. So this is a path that traverses the whole spanning tree. Every edge is crossed twice, once going down and once going up. So it's illustrated here, right? So this depth first search will traverse the whole spanning tree in about 2n steps, and what the hunter can do is just think of this traversal as a cycle. This is a thank you. So think of this traversal as a cycle. So if the hunter plays as if he's playing on this cycle, we know he will capture in time n log n. And the fact it's not really a cycle, but that it means that certain vertices that are distinct on the cycle are identified in the spanning tree. But this just means that the hunter might bump into the rabbit even faster on this graph than on the cycle. So the upper bound of n log n still applies. So the answer is there are graphs with n log n, like the cycle. There certainly are many graphs where the answer is linear. So for instance, if you have an expander graph, then the hunter can just do a simple random walk, and that will capture in linear time. Or obviously in a complete graph, the hunter and the rabbit are equally powerful, and so there the capture time is linear, just going to a random site. So the answer to this question depends on the graph. It varies between n and n log n. But here is an open question I want to go to. Let's see if it's mentioned here at the end. Yeah, I want to emphasize this question in blue. We said that on any graph, the hunter can catch the rabbit in n log n. Now, suppose we weaken the rabbit and make the rabbit also respect the edges of the graph. So now the rabbit and the hunter have the same rules. At every step, they can either stay in place or walk to a neighboring vertex. In that case, I would conjecture that the capture time is always linear, always order n. And with the unit, say 10n is a bound for all graphs, but we can't prove that. And what's missing is some kind of classification theorem that will distinguish graphs that are essentially one-dimensional. Like on the cycle, sweeping works great now against this weak rabbit. Just start a random location, sweep, and it's very easy to show that the rabbit is going to be caught in a round with constant probability if it can't jump more than one. And so constant number of rounds will lead to capture on the cycle. On the other hand, on other graphs, then you have to employ other strategies. So far, I've been able to verify this. We've been able to verify this conjecture in any specific instance by some ad hoc construction. So if you're on the binary tree, you have to do something. If you're on this graph, you have to do something else. And it seems to be always linear time against the weak rabbit, but we don't have any theorem to that effect. So that's maybe a nice challenge. Finally, the question mentioned on the top, there is a major open problem on which Bourgain, Tom Wolfe, Terry Tao, and many others have worked on, which is to understand Kakeya sets in 3 dimensions or higher dimensions. There's a conjecture there that all the Kakeya sets must have. So again, the Kakeya set in RD would have line segments in all directions, there. And it's easy to build a Kakeya set of 0 volume just by taking the planar Kakeya set and lifting it, right? Take that product with a unit segment, you'll get a Kakeya set in R3 with 0 volume. But is there a more interesting construction? Is there something of dimension, Hausdorff dimension lower than 3? So this is open, and unfortunately, it doesn't seem like these constructions, help in that direction. So you can do something like this with multiple rabbits and multiple hunters, and I've played around with this, but I didn't get any, novel things on Kakeya sets in higher dimensions that would help on that conjecture. Thanks for your attention.